So how many of you could manage to do the assignment that we said we should do last time? Nobody's done that? Yeah? So can you show them what you've done?
Should I show it through your email? I've mailed it to you.
Okay. So you want me to open the email here?
Yes.
Okay. So Revati has done this assignment for us, and Revati will explain to us how this has been done.
So first, we have the data that Sir had given. Some people want to add.
Okay. So I'm sharing the screen now. Yeah? Okay, now start. Sorry to trouble you.
So we have the data that Sir had given. We had scores of 10 students of maths and literature both. So we had to see the covariance between these two scores of each of the students. So first I read the data in on R that we had gotten on Excel, and after that I ran the covariance function for that data that I read it, and after that I got this table. So we basically have to see math, literature, the covariance, which is 7, that is a positive relationship, and therefore we can say that the students that score good marks in maths score good as in literature as well, and vice versa. So the ones who will score bad in maths will score bad in literature as well, and that's why we had 3 options that we had to choose from. So the conclusion would be that we have to teach both the subjects to all of the students.
Yes. Okay, thanks. Also, Revati is submitted, then Dhanashri is also submitted. Who is Dhanashri? Dhanashri is not there today. Right, so I'll also show you, I'll take you through what Dhanashri is also sent, which is also good. Thanks, Revati, for. So what Dhanashri has done is, Dhanashri has sent this assignment. Right? Let me share this. You can share this, right? So what she has done is, here is the calculation. Okay? So what do? You have got the data x and y. You find the sum. So why don't you guys do this along with? Right? So you have all the data from yesterday, last time? Pallavi, you have the data?
No sir, I don't have the data.
Okay, I gave the data last time, no? So you can now open your Excel and say, basically what you have to do is find the covariance between marks in maths and marks in literature. Yeah? So X is the marks in maths, Y is the marks in literature. Right? So these are the marks out of 10. 6, 5, 7, 8, 2, 4, 1, 0, 9, 8. Right? And the sum is 50 and the marks in Y. And this is the mean. Right? So do it. Unless you do it, you'll never know. Can you ever go to a class for making cakes and never actually bake a cake? No, you have to go there and make a cake, no? Tailoring class काहीतरी शिवायला लागेल ना? Similarly, you'll have to work here to do something. You done it? आत्ता केलं. Okay, but so x and y, you are getting all these answers. You have to calculate x minus x bar square, y minus y bar square. So first take x and y, find the mean of x and y, then take x minus x bar square, y minus y bar square, right? For each value, sum them, right? Multiply them and divide by n minus 1. Okay? What is n here? 10. So what is n minus 1? 9. Right? And so you got the covariance, like Revati got, the covariance here is 7. The answer is right. She has to make sure that you get this answer. Okay. अरे yeah. Right, so first calculate the covariance, and then Dhanashri has done something very interesting. So I'll show you the next screen. Who is Dhanashri? Ah, you got a good assignment. Thanks. Right. Because what she has done is a little bit extra. Right? Yeah. So are you getting the answer covariance 7? काय हो it goes much beyond that, but there are some numbers that you can hang a debate on. Exactly, the example म्हणून दिला आहे. But the question is far deeper than that. Very true. This is just a teaching example basically. Yeah. Absolutely. Question is far deeper than that. आलं सगळ्यांना? Are you getting the answer? All those online? Pallavi, can you do it? Hello?
I'm getting these numbers, yeah.
Okay. But are you getting covariance 7?
Sir, no, like I am in the last step basically.
Okay, so basically you have to multiply all those and then divide by n minus 1, right? Yeah, the number that you get 63, you have to add all those numbers and sum will be 63 and then divide by n minus 1, right? Now why do we divide by n minus 1 and not n? Degrees of freedom, because we have now actually already calculated the mean. So there are n observations, there are only n minus 1 observations which can vary independently. And we are estimating a number. For estimate, we are making a guess. To make a guess, what is valid is only independent information. Redundant information has to be thrown out of the window. We don't need it. Right? Sure? Okay? Because Pallavi, we have to divide by the right degrees of freedom, right? The degrees of freedom are here n minus 1, the number of independent information bits. So we said last time that if you have n data points and if you calculate the mean, then there are only n minus 1 independent deviations from the mean. And we are trying to estimate the product of the independent deviations from the mean. So we want an average of that, no?
Yes.
So what are we really doing? We are trying to say, okay, we want an estimate of the deviation, estimate of the deviations from the mean. So we say if you have many independent deviations from the mean, we aggregate them, then we'll get an estimate, like time on the watch we said last time, right? And then we have to look at how many of them are independent, how many of them are independent, give you information on their own, n minus 1. Yeah? Right? If I give you a Bengali paper and an exact English translation of the Bengali newspaper, will that English translation give you any more additional information? It won't, no, because it's just the exact translation. So you don't have two newspapers, you have only one newspaper. Yeah?
Yes.
Right? So right, folks? So 7, it means that the covariance is positive. If you look at the number, you see most of the products here are positive, right? And a positive meaning that they are the same sign, by and large. Which means that whenever x minus x bar is negative, generally y minus y bar on average is negative. Whenever x minus x bar is positive, by and large y minus y bar is positive. So we are moving in the same direction. Okay? Right? Sure? Now, if you look at it geographically, graphically, you can actually see the relationship. On the x-axis you have literature scores, on the y-axis you have math scores. And if you actually plot a scatter and if you draw a line, then what you see is a straight upward sloping line, right? So generally more math scores, higher math scores means higher language scores. And how would you do that? You see the code here. Right, so try to draw this picture. Try to draw this, then we are going to come to a very important idea after this. The idea of normalization, standardization, and how for standardized data, covariance becomes correlation. Somebody joining now? Yeah? So now draw this. Get this exact graph so you can show the positive association between the two variables. मोठा करू का? Sorry. Is it clearer now? So plot this.
Sir, I have one question.
Yeah, Pallavi.
So like when you are trying this code like ggplot data AES, so these names, this literature and maths, so they have to be in the same format as it is in the like CSV file.
Yeah, because otherwise, how will the computer know that that is the name of the variable, no?
Okay.
So if your name is spelled in a certain way on your bank account, and if I give you a check with some other name, right, will it go?
This is an individual.
Yeah, so spelling exactly, everything has to be the same. Are you getting this? Graph ala hai?
And sir, what about the order inputs? This y and x variables are being placed in the.
So because we want so basically in the graph, we want literature on the y-axis, right? And maths on the x-axis. But if you want to interchange that, then you can interchange that depending upon what you want to put on the y and the x-axis.
So I'm not talking about this changing this. I'm just saying like if I write x equal to maths.
That's fine. That's fine. No problem.
Okay.
The file name will be different for you, right? Read.csv. Ala graph. Same nice blue colored one. That's how the Economist magazine would do it if it did that. If you write theme understroke WSJ, then the Wall Street Journal theme will come. If you say theme understroke Stata, then the Stata theme will come.
सर RSW covariance प्राइम नहीं हो
ना रे तू हा डेटा है ना. This is the data, right? You have to save it as a CSV file, na? For your whatever name you have. No, this is the file which she has given, but you can have some other name for where you have saved the data, no?
ओके
You have to save it as per your name.
So what does this SE equal to true mean here? Like geom smooth pattern element.
So standard error. So what we have, Pallavi, is, you see there is this line that we have got, correct? It's the estimated line, no? But because it's an estimate, it could have been a little here and there, right? So there is some uncertainty in these estimates. And these are called standard errors, as we'll learn about that. So this cloud that you're seeing, this gray color, it is that uncertainty. That line can be anywhere here. Okay? So that's why SE is equal to true.
Okay.
Dala? Everybody's got the graph? How many of you got the picture? Right? Everybody's got it?
I'm just like on the end of this code.
Yes, wonderful, Pallavi. So once you have done this, have you been able to read the data in whatever CSV file you saved it?
Again, sir, one clarification.
Yeah, Pallavi.
Just that's this left title. So these X and Y names that you are putting, so they can be any names, right?
Any name, any name.
Okay.
Done? Have all of you been able to do this? Yeah? Hello? Everybody here?
Yes, sir.
Sure, now, so we understand what covariance means, right? Now,
Okay. Can you show the code once? I'll just,
yeah, here, Pallavi.
Okay, sir. So this limit, I have not understood, sir. Like X limit 0 to N.
So basically, if you don't do that, see, if you look at the data, Pallavi, the data is starting from the X and Y values are starting from, X is starting from 2, right?
Yes.
Okay, Y 0. So basically it says that X axis should have a limit from 0 to 10 and the Y axis should also have a limit from 0 to 10. If you want to show the graph only from say 5 to 10 on the X axis, then you will change X lim to 5 comma 10. Okay? Everybody got this? Okay. Now, because then it means some bracket is incomplete in your case. So if that means that some command is incomplete, if there is a plus. So some bracket must have remained. Yeah, so math score is a comma taklas. Pardon? Here is the data. Yeah? Allah? Okay, so now I'm going to go to the next point, right? So please look at my Excel sheet now. Okay, I'm going to open an Excel sheet and bring to you the next important point, right? So suppose I now have say marks, say literature marks, and say maths marks, right? And suppose this is a test out of 10 marks, okay? Assume that test out of 10 marks and these are the kind of marks that students have scored, right? So I got 8 students. So they're the marks, right? Okay, now let me find the covariance for you first. So find the covariance for me with again. Right, so this is the mean, right? So L minus L bar and say M minus M bar, right? So L literature minus literature bar, M minus maths bar, right? So what do? I take A2 minus $A $10, right? And then so basically it takes each value of on the column A and subtracts it from the value in column A row 10, right? So to fix that you have to write $A $10. Yeah? Okay, similarly I have to do here, right? What do I have to do here? I have to do B2 minus $B $10. I drag it down and I have this, right? Sure? So L minus L bar, right? Okay, and then I multiply the two, right? Product, right? So what I do is basically C2 minus D2, I do this, control C, control V, and then I sum this, and divide by, I've got 8 observations, so I divide by 7, right? Okay, it says 0 covariance, right? Okay, so let me change this value a little bit, because why is it giving me 0? Oh, sorry, C2 star D2 it should be, right? And this is divided by 7, right? So the covariance is minus 1.07143, etc. Right? Sure? Now, suppose what I do is, now listen carefully. Right? Let me also calculate here the variance of L. Right? Okay? So variance of L, just to show you an important point. Right? The variance of L, what do I have to do? C2 star C2, sum all this, get it here, right? Sum this, right? So control C, control V, right? So this is the sum. So this is the variance of L, and this is the covariance between L and M. Everybody gets this? This is the variance. So all that I did was you have to find the variance of L, no? So you have to square each of the deviations from the mean, sum them, and divide by n minus 1. So C2 into C2, C3 into C3, so on, right? Okay, so this is the variance, this is the covariance. Yeah? Right? Now, look at it. Now suppose I said that this test should not be out of 10 marks but should out of 100 marks. So 4 out of 10 means 40 out of 100. 4 out of 10 means 40 out of 100. 6 out of 10 means 60 out of 100. So I rescale all these 40, 60, 50, right? 40, 60, 70, 40, 60, right? This has become 70, this has become 30, this has become 40, this has become 30, this has become 40, this has become 60, this has become 90, and this has become 20, right? Sure? What has happened to the covariance? What was the covariance earlier? If I do this again, just see what the covariance earlier was, minus 1.07. And the variance was 1.35. Just write these things down. Just write down what was the covariance earlier, minus 1.07, and what is the variance earlier, right? 1.35, right? Sure? Now I am rescaling all the data. So this becomes 40, right? Because I am only changing the scale of measurement, right? The exam was out of 10, now I am making it out of 100. So 6 out of 10 is 60 out of 100. Yeah? So what is the new change now? When I rescaled the data, what has happened to the covariance and what has happened to the variance? What was the covariance earlier? I multiplied x and y both by 10. What was the earlier covariance? Minus 1 point. Now what is the new covariance? Minus 107 point. So how much is the decimal point moved? By 100. 100 times, right? So 10 square. So the covariance has changed. The only thing that has remained constant is the sign of the covariance. It was minus, still continues to be minus, but the quantity had changed. So the important thing that we have here is the covariance will only tell you what is the direction of co-movement. It will not tell you anything about the magnitude of the co-movement, because the magnitude here is dependent on the units in which you are measuring the data. Actually, nothing has happened to the relationship between maths and literature. Are they different students? No. Are they being given a different test? No. Same marks have been rescaled. And the covariance has changed so dramatically. And you also see that the variance is also changed by the same amount. Right? Can you quickly see the algebra there? What's happening? The column E is a product of C and D. If I change all values of what is C, A minus A bar. If I change all values of A multiplied by 10, then all values of A get multiplied by 10, A bar gets multiplied by 10, so the gap gets multiplied by 10. So all values in the column C have got multiplied by 10. All values in the column D have got multiplied by 10. So the product has got multiplied by 10 square, which is what? Which is 100. And so you see the covariance has changed from minus 1.07 to minus 107.133. So the covariance only tells you the direction of co-movement, not the magnitude of co-movement. That is because the covariance depends upon the scale of measurement. And the same thing has happened to the variance. Because what is variance? It is the sum of the squares of the column C. So if all values of C increase by 10, all the squares will also increase by 100. All the squares will increase by 10 square. Each value is being multiplied by 10. So the squares will get multiplied by 10 into 10. 10 square. Right? So what you have at the bottom is therefore the same thing has happened. And which is something that should worry people, right? Because the covariance tells you only the direction but not the co-movement. Then you can still say that maths and literature are moving in opposite directions, but how strongly? Whether maths and literature are moving in the same in opposite directions more strongly than the relationship between science and literature. You want to see the strength of mechanism of the relationship also. And that cannot be done by the covariance. Right? Sure? Okay? The covariance is not unit free therefore. And so we have a problem with covariance. Right? So, how does one think around this? There's a man called Carl Pearson who began to think about this. Right? Have you heard this name, Carl Pearson? Yeah? You should read his biography. It's a very interesting biography. Carl Pearson used to work in a laboratory called biometric laboratory, which was set up by a man called Galton. Do you know who's Galton? Galton was the man who first coined the term regression, right? Okay, but Galton was a cousin of Charles Darwin. And that time Darwin's ideas of the natural selection in the natural world were making waves. Right? Suddenly it said, no, God has not made the universe, but the universe is really evolved by, constantly finding new forms. And everybody thought that those ideas could apply everywhere. So Galton thought that they could also apply to people. Right? Which it doesn't really apply, right? Okay, so Galton began to set up this biometrica laboratory, where they did all kinds of experiments on trying to understand why European races, naturally, because they thought the evolved races were European and all the races were backward. So they started to look at all kinds of studies between, facial features of Europeans and facial features of Africans, and they began to argue that how, for example, facial features of Africans are very similar to mentally disabled Europeans, and all those kinds of literature began to come about, right? And Pearson was a major driving force of that literature. So that literature began to be called eugenics later on, right? Which led to very serious consequences during the Nazi rule. And a lot of statisticians were avowed eugenists. For example, R.A. Fisher was a very strong believer in the racial theory of evolution. Right? In fact, he wrote to the British government. He said that because he is brighter than everybody else, and he has had 6 children or something, so the government should pay for his children because he's improving the British race apparently. Right? Okay? So you had such kind of characters, but if you go to the Mumbai University Library, there they have, this biometric laboratory journal called Biometrica. So if you go to the Mumbai University Library, I'm sure Gokhale Institute also has that. The earliest issues of Biometrica journal are there. So there are strong studies of covariance between facial features of African skulls, and it's horrible, right? But fortunately that whole thing died out and they found that it doesn't work that way. Natural selection is a very different idea, right? But so basically that is Pearson was thinking about how to solve this problem, coming back to it, right? So the first thing that we'll do is, we'll actually try to make sure that so how would you actually solve this? If you had a way of saying that these series L minus L bar and M minus M bar do not change even if you change the scales of literature and maths, then the answer here will also remain unchanged. Right? If you could find a way in which whatever you multiply literature and maths with, if the resulting L minus L bar and M minus M bar did not change at all, right? Then you would get a way of making sure that this quantity, the covariance does not depend upon scale. Right? Sure? Okay? Yeah? Is this clear? So we'll try to see how that can actually be done. So I'm setting this back to the original values. Yeah? I'm setting this back to the original values. I'm now going to create, so this is the variance, right? What I'm going to do is, I'm going to create a new standard L. So I'm going to call it standardized, right? I'm going to standardize L. What do I mean by standardizing? I'm going to take each value of literature, so A2 minus, of course, the mean. This is what I had, and I'm going to divide it by the standard deviation of literature. Yeah? Standard deviation of literature, right? I'm going to divide this by the standard deviation of literature, right? If I divide by standard deviation of literature, what do I get? The square root of the variance, right? So let me, or even better, let me just find out here, let me just find out standard deviation of literature. This is standard deviation of literature, this is standard deviation of maths. Right? Okay, as you will note, if I multiply each value by 10, now see what's going to happen. Now this is probably a very important statement, so pay attention to this. If I multiply all values of this by 10, so if I kept it like this, what is the mean? 5.25, right? And what is standard deviation? 1.16. Now I'm going to multiply each value by 10. What has happened to the mean? The mean has got multiplied by 10. And what has happened to the standard deviation? It was 1.16 earlier, it's 11.6 now, right? So the standard deviation also is multiplied by 10. Why? Because the standard deviation is the square root of the variance. Variance got multiplied by 100. So the simple insight is, if I take L minus L bar, right, and divide, so I take each value of L, subtract from it L bar, and divide that value by the standard deviation. If I multiply all values of L by 10, the numerator will get multiplied by 10, the denominator will get multiplied by 10, and the resultant will remain unchanged. Yeah, you see this point? Right? Okay, this in fact has a name in statistics called standardizing the data. So it removes the influence of the units of measurement on the data. Right? So for instance, if I do this here, I'm going to do this here, L minus L bar, and I'm going to divide this by $A, $11, $A, $11, right? And similarly, M minus M bar, $A, $11, right? Yeah?
Which standard deviation formula like have you used? Like is it standard deviation for the population or for the sample?
No, standard for this data, no, Pallavi?
Yeah, yeah.
Right. So I get this, and now, so is the square root of the variance. I take this formula, I copy it down. Right? Yeah, you get this? So now, even if I change this, for example, to 4, 6, right? 5, 4, 6, 7, 4, 6, right? Okay, now look at the value. So if I change this to 40, right? A2 minus $A, $10. If I change all values now 60, if I change all values to 50, if I change all values to 40, if I change all values 60, which 7, 40, right? 60, right? These values still remain unchanged, no? Yeah? You see the point? If I changed all values by 10, this L minus L bar still remained the same. So note this, 0.9, for example, the first value of M minus M bar divided by standard deviation is 0.19314, right? Now I'm changing all values, right? 70, 30, 40, 30, 40, 60, 90, 20. First values remain unchanged. So all the products have remained unchanged, right? And this covariance that you got is remaining the same. Yeah? Are you getting this answer? You getting this point? So basically what do I do is, I standardize the values and then find the covariance, right? Okay, in fact, if I standardize the values, what do I have to do? Actually, I don't even have to do this. All that I have to do is I got this product, right? And then I have to simply sum this, right? And divide by 8. I get this value, right? Sure? Minus 0.69. So what have I done? Earlier my problem was that the data depended upon the scales of measurement. If I change the units of measurement, the data changed. And so covariance changed. Now I transform the data in such a way that it doesn't depend anymore on the scales of measurement. And then I find the covariance. So if you do this, right, when you find the covariance from standardized data, it has got a different name. It's called correlation. It is called Pearson's coefficient of correlation. And the important thing that I have just demonstrated is that the Pearson's coefficient of correlation does not depend upon the units of measurement. So it's an improvement over covariance. Not only does it tell you the direction of co-movement, but it is because it's not variant to the scales, it can also tell you the direction, the strength of the co-movement. Right? Sure? For example, the highest possible positive correlation is said to be +1. Right? Highest possible positive. So what is the formula? We are doing x minus x bar, y minus y bar, divided by standard deviation of x into standard deviation of y. We are multiplying all those, no? Right? Right? Covariance divided, so you take the covariance, divided by the standard deviation of x, standard deviation of y. Right? You take in the numerator of the covariance and you divide by the standard deviation of x, standard deviation of y. That's what you get. Right? Okay, now, suppose x and y are the same variables. So summation x minus x bar, y minus y bar upon n minus 1 divided by standard deviation of x into standard deviation of y in the denominator. Now if x and y are the same variables, then in the numerator you will have x minus x bar into x minus x bar upon n minus 1. So what will the numerator become? Variance. In the denominator what will you have? Standard deviation of x into standard deviation of x. So Standard deviation x, the standard deviation of x square is nothing but the variance of x. So numerator is variance of x, denominator is variance of x, and the resultant is 1. Correct? So the highest possible positive correlation is 1. Yeah? Huh. So, and no other variable can have a more correlation than itself, right? So that gives you the limit on the upper right? Now no variable can have stronger negative correlation to x rather than compared to minus x. So instead of think of y, think of minus x. So what will you have in the numerator? X minus x bar minus x minus minus x bar. Right? I can take the minus outside the bracket. So on the top I'll have minus x bar into x minus x bar upon n minus 1. So minus of variance x. In the denominator I'll have standard deviation of x into standard deviation of x. Because standard deviation of x will get multiplied by minus 1 square, which is the same, which is just 1. So you get minus of covariance of x with itself, with minus variance of x upon the variance of x. The answer will be minus 1. Yeah? So the highest negative correlation can be minus 1. So correlation will range between minus 1 to plus 1. Which means that closer you are to plus 1, more stronger the positive relationship. The closer you are to minus 1, the more stronger the negative relationship. Yeah? अरे एकदम इम्पॉर्टंट पॉइंट में जाता है हे परत सांगायला पाहिजे ना कारण इम्पॉर्टंट आहे त्यांना कळलं नसेल. I told you I once wrote a article criticizing Mr. Bill Gates. तब से गूगल ऐसा करता है. The jokes. So point taken. What is the difference between covariance and correlation?
In correlation, you also understand the strength of the relationship,
Yeah.
not just the direction.
The covariance is dependent on units of measurement. So first you standardize the data and calculate the covariance, you get correlation. Right? Sure? Acha. Covariance is a mean. Variance is a mean. So correlation is nothing but the ratio of two means. Law of large numbers again works. Sample covariance, correlation will go to population correlation. Yeah? That's why what you get from the sample as a sense. If you increase the number of data points, you will get closer and closer to the true population value. Yeah, folks, I'm sorry you missed an important point. Right? Till what point were you there, Pallavi? Hello?
Hello, sir. Yeah.
Yeah, I think we lost connection for a while. So what point, till what point were you there?
You were discussing about this, this rescaling, like it's
Yeah.
not getting, the correlation is not getting affected.
No, so covariance is now the relationship. So basically the variables, the deviation of x from x bar divided by the standard deviation is remaining the same, right? Yeah? Is this point clear to everybody? Yeah? Hello? Yeah? So basically what we said was that because covariance depends upon the units of measurement, if you rescale the data so that they are independent of the units of measurement, and then if you calculate the covariance between them, you get what is called the correlation coefficient. Where's Pearson's correlation coefficient, right? And now that doesn't depend upon the scale of the data or the units in which you are measuring the data, right? More important, further, the highest possible positive correlation is +1. Why is it +1? Because I'll again show you the exercise. So I'm sharing my screen again with you. So this is the data I have, right? Now instead of say maths, suppose I had the same marks in maths and literature, right? So these were 40, right? These were 60, these were 50, right? This was 50, this was 40, this was 60, this was 70, this was 40, right? And this was 60, right? Okay, so the mean and everything is the same, right? Sure? Right, so let me just take the average of this here. Right? So correlation is an advantage. Some very fundamental ideas in statistics, okay, which we are going to use a lot. हे कळलं तर regression लगेच कळणार आपल्याला. Once you understand that covariance idea very well and correlation idea very well, basically regression is about looking at co-movements, right? So we'll quickly done that. And R has very nice ways of standardizing data. So we'll spend some time on showing how we can beautifully visualize correlation graphs. Yeah? Okay, so that you'll feel very nice about As you can see, literature and maths, right? If the marks were the same, the correlation is also the same, right? Correlation is also 1. So if x and y are the same variables, the correlation will automatically become 1. Why? Because in the numerator you will have the variance of x, in the denominator also you will have the variance of x. Right? Whereas if say marks in maths were exactly opposite of marks in literature, right? They were exactly minus 50, right? Suppose these were some, assume that minus marks are also possible, right? So correlation becomes minus 1. Yeah? Correlation becomes minus 1. So
screen is not visible.
Screen is not visible. Oh, I'll just put the screen back again. अरे सविता आपण ह्याच्यात कुठे आहोत ते हेच नाही आहे गुगल मीटच नाही आहे ओके इथे आहे का नाही ना क्रोममध्ये फर्स्ट विंडो ओके राईट Yes, you can see this. So if suppose maths and literature were the same numbers, can you see this now? Akash, this there?
Yes, sir.
Okay. So if x and y were the same numbers, the correlation becomes equal to 1. Right? So highest possible correlation is 1 because there can't be any stronger correlation than when x and y are the same numbers, right? And if y is exactly minus x, that is the strongest negative correlation that you can have, right? Then the correlation becomes minus 1. So the importance of correlation is that tells you not only the co-movement, but that strength, the direction of the co-movement, but also the strength of the association. Yeah? Covariance only tells you the direction because covariance depends upon the scale. If you change the scale, so what do? You rescale the variables so that now they are no longer dependent upon the units of measurement. Right? This is called standardization. So when you are doing any analysis in statistics, and if you are worried about the things being measured in different units. So for example, you have prices of say apples. You want to compare the price of apples in America and price of apples in India. Price of apples in our Gultekdi market will be measured in rupees. Nobody will tell you prices in dollars, right? And the price of apples in New York will be measured in dollars. So something will be in dollars, something will be in rupees. And comparison will be a problem. So first step you should do is standardize. Right? Standardize. So take each value, subtract from it the mean, divide by the standard deviation. Right? That is called the Z-score. Right? Sometimes in statistics it's called a Z-score. Each value of x minus the mean divided by the standard deviation. Right? It's called a Z-score. Right? So convert both the standardized and then do whatever analysis you want because then you're sure that your analysis is not dependent upon the units of measurement. Right? Okay? Is this clear to everybody? Pallavi, any doubts?
No, sir, this is fine.
Fine, wonderful. So now I'll go to show you some very nice ways of making graphs, right? in R, showing this very nice pictorially in a way which people will really like, right? Okay, R has some of those very nice capabilities, right? So I'm now I'm opening a new library, new file, right? Okay. And I think the name of the package, right? So there are many packages to do, right? Okay, so okay. Okay, so we'll now use a package called corplot. Corplot, CORRPLOT, right? So go to Tools, Install Packages, CORRR, I think. No, CORRPLOT, right? Corplot. Right, the library you have to have is Install Packages, Corplot. Yeah? Yeah, have you done that? Install, right? I have done that. Install. I have installed corplot. Now I call library corplot. Yeah? Okay. Now there is a package called empty cars. Okay, what is this? So, if you want to see what this empty cars data set is, okay, it's a data set which we'll be using. Alright? Help empty cars. It says it's a motor trend car test, right? What is this? Data is extracted from the 1974 Motor Trend US magazine, fuel consumption and 10 aspects of automobile design and performance for 32 cars. So what is the data on? Miles per gallon, that's fuel consumption, number of cylinders, right? Some cars have 3 cylinders, 4 cylinders and all that. Displacement, that's the engine size, horsepower, rear axle ratio, weight, right? 1/4 mile time, engine, whether it's a V-shaped engine or a straight, transmission, whether the car is automatic or manual, number of forward gears, number of carburetors. We don't have to be ingenious for that, just think that these are some numbers. Savita is already looking worried about what these numbers mean, right? But nobody's asking you to open the engine, car engine. Just kind of, this is just an example for class. Nice, it gives you the example is nice. So what we want to do is, so you're going to view this data, view empty cars, right? So what do you have? Say Mazda RX-4, miles per gallon, cylinders, displacement, horsepower, draft, weight, right? Cusack, I don't know what is, right? It's got 4 gears. How many carburetors? 4 carburetors. Yeah? Right? It's an automatic. AM is 1, right? So whatever that name is. Now, I want to calculate the correlation between all these variables, right? I want to calculate the correlation between all these variables. So what do I do? Okay. So let me I don't want to see this anymore. So M is equal to core empty cars, right? And if you run this, and if you say M, it has given you all the correlations, right? So if you, for example, view M, what does it tell you? So correlation between miles per gallon and miles per gallon. Correlation between miles per gallon and cylinders. Yeah, correlation between miles per gallon and displacement. So what does it tell you? That cars which have a bigger engine have a lower miles per gallon. Cars which have a bigger horsepower have a lower miles per gallon, and so on, right? Sure? Don't worry so much about these numbers because we're not going to take any policy decisions on cars. We're just trying to understand what these numbers are. Right? So this is called a correlation matrix. Everybody gets this? Everybody's got these numbers?
Yes.
The folks in the Antarala? Got this?
Yes.
Yeah, okay. Right. So now we just want to kind of visualize this, right? Because if you show these tables to anybody, they're going to be really bored, right? Okay. So now what we're going to do is we are just going to do a plot. Core plot. What do you want to plot? The object M, right? And what do you want to show? The numbers. Right? So the correlation values. Right? So if you do this, I need to also give some other information, I think. No? Oh, sorry, not numbers, number. Yeah, number. Right? Core plot number. Yes, it's not looking like a very clean graph because a lot of things, but basically the numbers. So MPG, all these numbers are being plotted here. Right? I can make these numbers smaller. Right? Yeah? So how do you make these numbers smaller? Find out. How will you make these numbers smaller? They're looking very cluttered there, no? They should be smaller. The font should be smaller. Do some R&D now on your own and find out what needs to be done to make those numbers smaller.
Will you specify the size?
Where? So how will you, so just type, go to Google and say core plot function in R. Yeah? Go to our dear friend Google and say core plot function in R. Right? Core plot, right? So, how will you now find out, how will you kind of change the size? There's exercise for you.
So core plot M, method number order is equal to H plus number dot CEX is equal to 0.5.
Correct. Yeah? So you see all these things here. You can add title, you can add everything, right? Yeah? These are all the various things you can control for. So do we write? Number dot CEX?
Is equal to 0.5.
Yeah. So if you say number dot CEX is equal to say 0.5, right? If you make a small thing, right? Looks a little better but not great, right?
So I have given 0.5 and it is coming out very neat.
Great. Yeah, it is actually when I zoom, right? It's coming out nice, right? Sure? Yeah? So this is much easier to see, no? compared to that table. Yeah, so make sure everybody gets that. Now, suppose it is MPG, I want these variables to be alphabetically arranged. Right, so AM first, right, then what starts from B second, C third, and so on. So that it gets a better structure. How will you do that? How
What
will?
do you want to do now? Like,
So basically these, I want to arrange these variables in alphabetical order. How will you do that? थोड़ा सा R&D खुद करना पड़ेगा अभी. Yeah? So if I say I want it to be ordered alphabetically, right? So if you look at the commands, it says order is equal to alphabet, right? Alphabet, correct? Yeah? Yeah? Sure? Now, look at that corplot help and you want to add a title to it. You want to add a title to this graph. Correlation between what, right? Correlation between whatever. Correlation exercise class 1, whatever name you give. Put a heading to it. Go to corplot function, look at its help. Because you also, see R, you don't have to remember all the commands. You have to know how to find the commands. Right? Good librarians don't know everything that's written in every book in the library. But if you want to, they can definitely help you. If you want to know something, they can definitely help you find the right book. Right? So it also be a kind of librarian with R. You have to know where to find what. I don't remember even a single command in R. I just know where to find them. Alan? काय केलंस? So it is simple like this. It says title is equal to first graph, say whatever name you want to give, and then it allows you to also control the size of the font for titles and everything. Yeah? Yes, so I have the first graph already. Yeah, first graph. It's going outside my window, but that's fine. Sure? Right, folks?
So what is the code, sir? Can you show the code once?
Pallavi, you have to find it now on your own.
Yeah.
I just told you how to find that, right? Here it is. Yeah? So instead of methods equal to number, if I say methods equal to color, right? Then of course this doesn't make sense, right? Because numbers are not being shown. So I just wanted to show colors. Yeah? Yeah?
Yeah, but this is a bit hard to read.
Right. All that it says is yes. So it says there's a scale here, no, Pallavi? So all the reds, the darker the blue, the stronger the positive correlation. The darker the red, the stronger the negative correlation.
Yeah, so the diagonal elements, that's why they are blue.
They're blue because all the correlations are 1, no? So basically, it's for some people, some clients I realized, or some people are really averse to numbers. When they see numbers, they feel like going home, right? But if you show the same thing in colors, then they understand. They are more willing to sit and look at it. Some people just have, when they see a number, they get scared. Whereas the number is telling you something. So if you show something behind the number, they're still happy with it. Yeah? This is not the only way to do it. There are actually even better ways to kind of show it. So I'll quickly show you that. So we say method is equal to circle, right? Go to from color. Say method is equal to circle. Right? Sure? If you say method is equal to pi, I think time for a tea break, I think. Yeah. So this I think is this is the easiest to read, Pallavi. Yeah? So the fuller the circle, the stronger the correlation. The bluer it is, the stronger positive. The redder it is, the stronger negative. Right? So you can see all these moons, full moons, up moons, etc. sitting there. Right? And you can easily read the correlation, no? Even if people who are numerically illiterate can see this. Yeah, because we are used to numbers. But there are a lot of people who are not used to numbers. I know some people who are very bright, but who have a form of dyslexia. Numbers just don't make sense to them, but pictures do. I mean, so they're phenomenally bright people I know who just can't read and write but they're very sharp. Right, so for them something like this you will tell them, okay. But ultimately the point is there are various forms in which you can do it. Right? And there are many packages in which you can do it. Sure, so what we'll do is we'll now take a tea break. We'll come back because we have evidence now that we need a tea break. Right? And then we'll come back and now do some tests of hypothesis. Learn about Z tests and T tests and chi-square tests and F tests and so on. Right? Sure, after the tea break. As you realize, when we started with this subject, we said that we want to know population parameters. But population parameters are not knowable. All that we have is information from the sample. The sample information is only a guess. It is a guess that depends upon the data that we have. So the data is the information. Right? Okay. Now we need so the information changes, the guess will change. Right? And therefore, our guesses, our estimates are random variables. Whereas what we want to know is not a random variable, it's a fixed parameter. Right? So then the question arises, what is the validity of looking at samples and making statements about the population when the two are different things? Yeah? And that is where the science of statistical inference comes in. That is where hypothesis tests become important. So what's a test of hypothesis? It says, okay, given the information, what can you reliably say, with what reliability can you state a hypothesis about the unknown population parameter? Right? So for example, if I make the statement that the per capita income in Pune is 50,000 rupees per year, what is the validity of this statement? And suppose he says that it is 80,000 rupees a year. then how do I check which of the two statements is more likely to reflect the reality? His is an estimate, mine is an estimate, right? So I need to kind of have a mechanism, a way of thinking, which takes me from the estimate to the actual population parameter. Because as we said, we are not interested in the estimate. We are interested in the actual population values. Right? Sure? And therefore, we need a way of thinking about what the true population values are from the sample information that we have. That is where the test of hypothesis come in. Okay? Okay. Now, we talked about the normal distribution in the last class. We said it's a distribution which has a mean and a variance. If you change the mean, the scale changes. If you change the variance, the shape changes. Correct? Right? Okay. Then, so I'll first draw a normal distribution for you. Okay. Right? Or before that, let me start a story. Now suppose, for God forbid, but for some reason you don't get any jobs after you complete your masters. Right? So you're looking for a job. So you start traveling from one state to another looking for jobs. First you look at it, Pune, kutne hota hai. Then you start going to Kolhapur, nothing happens. Then from Kolhapur you move on to Belgaum further to looking for jobs. Right, finally you go up, get to the Karnataka, Tamil, Kerala border. And there are lots of forests there. Right? And then you go to the Mudumalai National Park and you find a board there saying that people with training in statistics required urgently. So you immediately take your file and go to the range forest officer, the DFO's office, district forest officer. Sir, wo party pad ke main aa gaya. So, you know, one of my friends actually had a very interesting incident when party pad ke aa gaya. You see, what happened was, when I was studying in Ferguson College, there are a lot of jobs used to come. Opposite the Pune station is the main building. There are a lot of administrative offices, right? And that time there were no computer, laptops. They were just typing machines. So my friends desperately needed a job. And then he told me a very interesting story. He said, see, I went looking for that job. It said typist wanted. So I went to that office and they said, please let me. I thought typing to so power. They said, give me a job. They said, what do you mean? They said, I am a typist. They said, what is your speed of typing? So he thought high speed is good. So he said 80. Right? So that man was a little surprised. So bring a typewriter and make him type and see whether he can actually get 80 words per minute. I said, what happened? Arya, I did not know. No, numbers are not in order. Okay, I thought ABCD hoega. So that's not there. But do you guys know the story of these typewriters? Why they are not ABCD? No idea? Because and that's very funny, and that's a very important thing in economics. I think all students should know that. You see, ABCD, right? Earliest typewriters were rather clumsy, right? The keys, when you press them, wouldn't come back immediately. So keys would often get stuck, right? So Remington first experimented a lot and created a sequence of words where keys are least likely to get stuck in the English language. Right, so there are very few words in English language where Q, W follows Q and all that. E follows W. So those were times the keyboards came up. Those are called QWERTY keyboards. Right, but unfortunately now, even in the days of electronic keyboards, where there is no question of anything getting stuck, the QWERTY keyboard still remains there. It is. Right, and why is that so? That's called a lock-in effect, right? Why is it lock-in effect? Because historically, typists have been trained in typing QWERTY. And because they're trained in typing QWERTY, if you made a keyboard which said ABCDE, it won't sell. Right? On the other hand, as long as the keyboards are QWERTY, anybody who trained in ABCDE keyboards wouldn't get a job. Even when actually ABCDE keyboards would probably be more efficient now because people will know the sequence of words. Right? But because that's a lock-in kind of a thing, right? History then locks you onto something where nobody has an incentive to change from that. Yeah? Okay, fine. So suppose you go to that DFO with a file and say, oh, party bad ke aa gaya main. Huh? So he says, see, good, I wanted somebody. We have a particular problem which I want you to solve. So you said, what problem? He said, see, what has happened in our forest is, we have elephants in our forest. Yeah? And these elephants, generally they were healthy. But some disease seems to have happened to those elephants. And what happens with this disease, they don't die. Nothing really happens to them. Yeah? So he goes and says, nothing really happens to the elephants, but some of them become very thin and some of them become very fat relative to normal elephants. Right? So some elephants become very thin and some elephants become very fat. And unfortunately, we don't even know what virus this is, so we don't know what tests to do. We are doing all that, but currently, you see, when tourists come to our Bandipur National Park, they say, what is happening to the elephants? Some of them are all their bones sticking out. Some of them are so fat they can't even walk, right? And we are a little worried. So you say, sir, but I am not a veterinarian. I did some statistics. Why are you telling me all this? He said, no, what we want to is to help us identify elephants who are afflicted with this disease. Right? So you say, how do you do that? He said, no, there are no other outward signs. There is no blood test or anything. We have to go simply by weight. So he said, okay, what is the data that you have? So the field director of the forest department of the reserve tells you that, look, we have data only on healthy elephants, adult elephants, right? Healthy adult elephants is the data that we have. We don't have data on these ill elephants, etc. And what do we know from that data? We know that if you are a healthy elephant, 90% of the times, your weight of a healthy elephant will lie between 3 tons and 7 tons. The mean weight of a healthy elephant will be 5 tons, healthy, right? But 95% of the times, 90% times, let's keep it, 90% of the times, healthy elephants will weigh between 3 tons and 7 tons. Not every healthy elephant is exactly 5 tons. You can have healthy elephants who are fatter than 5 tons. In fact, some of them can also be 10 tons. They can still be healthy. But the chance of a healthy elephant weighing more than 7 tons is only 2.5%. A chance of a healthy elephant weighing less than 3 tons is only 2.5%. Right? Or say 5%, sorry. So the chance of a healthy elephant weighing more than 7 tons is only 5%. Chance of a healthy elephant weighing less than 3 tons is only 5%. 90% of the healthy elephants will weigh between 3 and 7 tons. Only 5% of the healthy elephants will weigh more than 7 tons. Only 5% of the healthy elephants will weigh less than 3 tons. They'll weigh between that. Right? This is the only information that we have. Sure? And I want you to help us identify elephants who are not healthy. Right? So you, being taught by me, think of a possibility. You say, sir, what we'll do, you tell me where those elephants go to drink water.
Hello, sir.
Yeah. Hello?
Hello, sir.
Yeah. Am I audible?
Sir, yes, sir, your voice is tracking. Not.
My voice is tracking?
Yeah, yes, sir. Not clear, sir.
Audio is not clear. Is it clearer now? Jitendra?
Yes, it's better now.
It's better. Okay. So basically, okay, so you said, tell me where those elephants go to drink water. I said, why? And you said, okay, what I want is a big JCB which will dig a trench. And what I want is a crane, right? And what I want is a huge weighing machine. And the field director said, why do you want that? He said, no, what I'm going to do is, on those way to the elephants, now I'm going to dig trenches. And the elephants will fall into those trenches. Then my crane will lift each elephant out, right? And then the weighing card will show you what is the weight of the elephant. Right, so what I'm going to do is, every time an elephant weighs more than 7 tons and less than 3 tons, I'm going to say this elephant is an unhealthy elephant. Because 90% of the healthy elephants weigh between 3 and 7 tons. only 10% of healthy elephants will weigh either less than 3 tons or more than 7 tons. Right? So whenever I find an elephant, गेला का परत?
ऑडिओ लॅपटॉपचा झालाय
On झालाय. Okay. So basically the story of elephants, right? So these people have not got a job, so they have gone to a forest and they're looking for a job, and they're told that this forest has elephants which have got infected with some virus, and the virus has made some elephants very thin and some elephants very fat, and they're told that we have only data for healthy elephants, and 90% of healthy elephants will weigh between 3 tons and 7 tons. There can be unhealthy elephants who are heavier than 7 tons, less than 3 tons. But heavier than 7 tons, only 5% of healthy elephants are heavier than 7 tons. Only 5% of unhealthy elephants are less than 3 tons. So you have now decided a strategy, right? You are going to dig a big trench, right? And when elephants fall into it, a crane is going to go and pick up the elephant, and there is going to be a big scale. And the moment if that scale shows the weight of the elephant between 3 and 7 tons, of the elephant 4 tons, you let that elephant go, right? You apologize to it and let it go. Right? But if it weighs less than 3 tons or more than 7 tons, you conclude that this elephant is not healthy, because only 10% of healthy elephants will weigh less than 3 tons or more than 7 tons, right? Okay? And so you want to send this elephant to a health camp, right? Okay? And now after a few days, the health camp people are very angry with you. That they say, this fellow is sending all healthy elephants here, right? Okay? What is the chance that you will send a healthy elephant to the health camp? 90% of the healthy elephants weigh between 3 tons and 7 tons. Whenever an elephant weighs less than 3 tons, only 10% of healthy elephants will weigh less than 3 tons and more than 7 tons. Consequently, you catch elephants, weigh them. Whenever an elephant weighs less than 3 tons or more than 7 tons, you cross that elephant with red paint saying, yeah, unhealthy. Send it to a health camp, right? What is the chance that you will send a healthy elephant to a health camp? 10%, right? Because 10% of healthy elephants actually weigh less than 3 tons or more than 7 tons, right? And you're catching elephants randomly, and whenever the elephant weighs less than 3 tons and more than 7 tons, you're going to send that elephant to a health camp. So in a healthy population, if you're randomly picking up elephants, right, 10% of those healthy elephants will weigh less than 3 tons or more than 7 tons but still be healthy. So your strategy is to randomly catch elephants and weigh them and send them to health camps, right? If they weigh less than 3 tons or more than 7 tons, 10% of the elephants which you pick up will be healthy but still be sent to the health camps, right? That is called type 1 error, right? So what you're really doing is, in your mind you are thinking...
Not that audible, so can you please louder?
I'm not audible?
Yes.
No, for me you are audible, sir.
Audible?
Yes, sir.
Pallavi, can you... Am I not audible now?
Yes.
Yes, thank you, Pallavi. Right. So basically what you're doing is, right, so think of how you're thinking in your mind. In your mind, you're thinking of the fact, your thinking is like this. You're saying, okay, this elephant is coming, right? Right? Unless I have evidence otherwise, I'm going to think of this elephant as a healthy elephant. What is the evidence that you're using? The elephant is either too thin or too fat relative to a healthy elephant. So when you find that the elephant weighs just 1 ton, then you are thinking, okay, the evidence that I have doesn't seem to fit well with the hypothesis that I have this elephant is a healthy elephant. Right? So your hypothesis that you have in your mind is that the elephant is a healthy elephant. You weigh the elephant, right? And if the evidence that you have, that is the actual weight of the elephant, does not contradict the hypothesis that you have. For example, the elephant weighs 4 tons. You say by and large healthy elephants are very likely to weigh that, so you let that guy go. But if you find an elephant who only weighs 400 kilos, 4 quintals, right? You say, array, is a very unlikely that a healthy elephant will weigh so. So the evidence that you have is against your hypothesis. So the hypothesis that you hold in your mind is the null hypothesis. You take evidence, you look at evidence, and you see whether that evidence is consistent with the hypothesis that you have. If the evidence is very different from the hypothesis, right, then you reject the null hypothesis. But here, there is a 10% chance that you are going to reject the null hypothesis wrongly. That is called the level of significance. Right? That is called the level of significance. Right? So, level of significance is the error, probability of an error that you are willing to commit, right, in your hypothesis testing exercise of rejecting the null hypothesis wrongly. Right? That is a type 1 error. Right? Statisticians call it type 1 error. Is the idea clear? You have a null hypothesis, right? You have a null hypothesis, and then you try to see whether the evidence that you have counters the null hypothesis. Is it consistent with the null hypothesis? Not with the null hypothesis. If it does not, it seems unlikely to be consistent with the null hypothesis, you reject the null hypothesis. Right? But if you cannot say that the hypothesis counters the null hypothesis, then you don't reject the null hypothesis, does not mean that you accept the null hypothesis. Right? I take a train every day from Chembur to CST in Mumbai. I don't, but I'm assuming. There's a man who sits next to me every day. Right? And he's dressed in a coat and all. He's dressed, formally dressed. Right? My null hypothesis is that he is a lawyer working in the Bombay High Court. And my alternative hypothesis is that he is a CA. Right? Sure? Now, given his dress and his bag and look up, etc., right? My null hypothesis, what I see doesn't seem to contradict the hypothesis that he is a lawyer. What I know looks consistent with the person being a lawyer, no? The way he dresses and all that. But does that mean that I can assume that he is a lawyer? No. Can I sit with him and say, what are your fees? I have this case going on. Right? Who told you I am a lawyer, right? Okay? Sure? So that's the fact that you don't have evidence against the null hypothesis does not mean that the null hypothesis is not true. Right? Suppose I Shanghai some of you, suppose I tie your eyes and everything and take you off. We travel for 2 days in a car with blindfold, you don't know where you're going, and I put you in a room, there are no sounds, anything, etc., etc., right? And if your null hypothesis, this is Chennai. You have no evidence against the hypothesis, this is Chennai. But it could be some room in Wagoli, right? Okay? So, you just cannot, this the fact that you don't have evidence against the null does not mean that you accept the null. So, you never say the null is true. You say that you can either reject the null or you fail to reject the null. Right? Type 1 error is the probability that you have with which you are willing to make a mistake when you're rejecting the null. Right? That level of significance is something you have to choose beforehand. Right? For instance, if the forest department calls you and says, you have been sending all these elephants to us, a lot of those elephants are healthy elephants, nothing wrong with them, but we have to feed them and take care of them. It's very costly to feed elephants and our budgets are very small. See, there are some other important things we have to do, but we are wasting money in this feeding all your healthy elephants, right? So please stop, reduce the number of healthy elephants you are sending. So what will you do? You will then go back to the data and say, okay, 98% of the healthy elephants weigh between 2 tons and 8 tons. So we'll be starting the 2 tons and 8 tons limits. And the probability of type 1 will only be 2%. Right? But in this you are probably making another mistake. There will be some elephants who are genuinely ill who you are missing out, which is called type 2 error. Right? Which is called type 2 error. Right? Type 2 error. Yeah? Okay? Is this clear? So type 1, type 2 error is clear to everybody? Right?
Which one is more like a kind of more useful?
Depends Pallavi on the context. Right? For instance, here, if the elephants are not dying and the elephants are not very rare animals and the money should be used elsewhere, forest department is really tight on its budgets, then I would be more worried about type 1 error than type 2 error. I'd be worried more about sending healthy elephants to to health camp over and above not sending, missing out on some elephants, right? But if the elephants were an incredibly critically endangered population, which are called the keystone species. So if that population vanishes, the entire ecosystem will collapse, for example, right? And if this disease that we have a highly contiguous disease, and saving the elephants were a priority and there was no shortage of funding, then I would say, okay, I'm fine with sending 15, 20, 30 elephants to the health camp, right? Doesn't matter, but I will not miss out on a single unhealthy elephant. For example, during COVID times, right? During COVID times, there was a lot of, when we did not have vaccines, and it was very important to kind of control the epidemic. Even if you sneezed, you were sent to a camp, right? Sure? Okay, because type 1 errors were very difficult to, type 1 errors are okay, but type 2 errors of missing out a infected person, letting that in the population was very costly. Sure? But then after the vaccines were invented, and type 2 errors became less costly, right? And people realized that they couldn't be spending so much on oxygen and putting people into those over years, right? Then they don't now just, even if you sneeze in public, nobody looks at you, right? That's because the government says, okay, we can have type 2 errors now, no problem, but type 1 errors are a problem. Right? Because if somebody sneezes, if you pick that person up and put him in some quarantine for 15 days without nothing happening, then that person is going to be very angry and the government is going to spend money unnecessarily, and that becomes more important to avoid, because now leaving an infected person in the public is not such a problem because now we have vaccines and everything. Okay. Sure, so it depends on the context, Pallavi, right?
And so one more follow-up question.
Right.
So if we look at like how to reject or accept a hypothesis.
We never accept an hypothesis, Pallavi. We reject or fail to reject.
Fail to reject?
Yeah.
So then, sir, I think that type 1 error is used, right? We are not using type 2 error.
No, type 2 error is not. Only type 1 error, the level of significance comes from type 1 error, right? Yeah. But type 2 error we have to be very concerned about, and I'll tell you what really leads to the type 2 error as we go on. Sure? Is this clear? Idea is clear? Okay. So now you're doing this and you are now happily catching elephants and all that, and after 15 days you find one more person from this batch, right? But that person now he doesn't have a crane and everything, he has a butterfly net and something hanging from his shoulder. So sir, idhar kya karta hai? He said, like you, I didn't also get a job, I also read that party, so I went there. Now they told me that yes, there is a problem here. You see, we have all these teak plantations in our forests, and these teak trees flower, no? How do trees flower? Only a specific kind of a wasp pollinates those, only then they flower. Right? If the teak trees don't flower, our forests will go to dogs. So, there is a wasp, and those wasps have got a disease, it seems. Right? That disease makes wasps either too thin or too fat, right? Okay, so they have told me that the weights of wasps are normally distributed. 90% of the healthy wasps weigh between 2 grams and 7 grams. The average weight of a healthy wasp is 3.5 grams, 5 grams, right? 5 point something, and 90% and 95% and 2% of the wasps will weigh less than 2 grams, and only 2.5% of the healthy wasps will lay more than 7 grams. So what I do is, I take this net, I catch wasps, I weigh them with this small scale, and whenever a wasp exceeds 7 grams or less than 2 grams, this medicine I'm supposed to give that wasp. So I'm doing this to wasps, okay? So you say, okay, all the best. You think yourself, you're currently sitting under a tree and elephants are falling. That fellow has to go and catching wasps, right? So you say, thank God I came first. Then after a while, you find one more student of your batch. He's wearing some gloves, okay? And he's carrying one big bag. So you say, what are you doing here now? I said, just like you, right? Okay, somebody told me you got a job here, so I also came. I read that board, I went to that person. That person told me, yes, there is a vacancy here. He said, we have got porcupines in this forest, and these porcupines have got some disease, and some porcupines have become too thin and some porcupines have become, so he's told me one limit. So I keep on catching porcupine, that's why this glows, right? I keep on weighing them, and when a porcupine is small, weighs less than this number or heavier this number, I can give this injection. Have you thought of giving an injection to a porcupine? Porcupines are likely to give you several. In the process of you are giving one injection to a porcupine. So you keep on doing this. Like that, then you meet the whole batch. Somebody has been given a job to catch squirrels and weigh them. Somebody is given the catch of chopping pigeons and give them. Right? So all of you then say, okay, let's get a get-together now. So you have a get-together. And then you start talking and you say, okay, what we have to do is now our batch, people don't seem to be getting any other job. So you form an alumni association. Right? Okay. And you say, okay, our future students will come. And so our future students, they have to know, no. Now that forest officer is telling us, for squirrels this is the limit, for porcupine this is the limit, right? But if he doesn't tell them, then how? They have to have information. No? So you decide to call, okay, you decide to publish a manual. In that every species, squirrels, this is the weight limit. Mice, this is the weight limit. Right? Crows, this is the weight limit. Right, giraffes, there are no giraffes there, but say porcupines, this is the weight limit. Like that you start to, and then you realize there are thousands and thousands of animals in this forest. The data is there on all of them, right? But how to make such a big manual, right? Then you start sitting down yourself thinking, "Arey, aisa acha hota, it would have been good if all the animals would have had the same limits." So whether you're dealing with elephants or ants or honeybees, or lions or tigers or sambar deers, you should have the same limits. If you have the same limits, then this whole problem of publishing a manual will go away. So if the weight of the sambar or bee or elephant is less than that limit or more than that limit, you send those to treatment, otherwise you keep them. The question is whether such limits can exist. Do you think they can exist? Standardize, right? Because ultimately the difference between a fly's weight and an elephant's weight is only the scale. Some of them are in micrograms, some of them are in kilograms, right? So you standardize all of them, right? And if you have a normal distribution, if you standardize it, then what you get is called a standard normal distribution, right? So I'll quickly show you how to do standard normal distribution and how to create that. Right, and how you can actually standardize the data in R, right? So the standard normal distribution is a very important distribution. It has an important property. 90%, 95% of the standard normal distribution will lie between minus 1.96 plus 1.96. 90% standard normal distribution will lie between minus 1.65 plus 1.65. Right? So you already have those limits. They're told to you beforehand. Right? So you don't need that manual. You just have to remember the standard normal. Right? And so what you're doing is you're basically catch an elephant. If the elephant weighs less than minus 1.95, gets that minus 1.95 standard. So for each elephant you will create a standardized score. The weight of that elephant minus the mean weight of all elephants divided by the standard deviation of elephant weights. That's called a Z score or the standardized score. And if this number lies less than minus 1.96 or more than 1.96, you'll send that elephant to a health camp. For squirrels, you'll do exactly the same thing. Standardize the data, each weight of each squirrel minus the mean weight of all squirrels divided by the standard deviation of squirrel weights. Number less than minus 1.96, greater than 1.96, Mr. Squirrel goes to hospital. Otherwise, Mr. Squirrel is led back into the forest. Right? Sure? Okay, so makes life much more easier. Once you standardize, that's why standardizing the standard normal distribution is a very important idea. Secondly, the second reason why it's an important distribution is it's a building block of all other distributions. So the chi-square distribution is derived from the standard normal. The T distribution is derived from the standard normal. The F distribution is derived from the standard normal. And I'm going to tell you how they're derived, right? Okay, but its important idea is that you need to know the standard normal distribution very well. Is the idea clear? Right, so now we'll do a standard normal.
This 1.65 minus 1.7 does not have unit.
No, no. Standard normal is unit free. Right? Okay. So now to what I like the most, drawing pictures with R. Yeah? Okay folks. So now इसको जाने दो. So basically if you now realize the correlation between X and Y is nothing but the covariance between the standardized versions of X and Y. The correlation between X and Y is nothing but the covariance between the standardized versions of X and Y. Right? Sure? Okay, now if you have a distribution which is standardized, right? If you have X minus mu upon sigma, that's a standardized distribution. What will be the standard deviation of such a distribution?
Is it 1?
Yes, exactly, but why? Can you give me some reason why it would be 1?
So mean of this distribution is 0. So like let's say if you apply the formula, so like kind of the mean is generalized to 0.
No, why would why would the mean of a standardized distribution be 0? Yeah, because the standard normal, the numerator is X minus mu, right? So very simply, X minus mu upon sigma is the standardized version. So if you sum all that, sigma will come out, 1 upon sigma will come out of the denominator. So it is X minus mu upon sigma. If you sum this, then 1 upon sigma is constant. It will come out 1 upon sigma into summation X minus mu. And we just saw in the last class that the sum of the deviations around the mean is 0. So any standardized variable will have mean 0. Right? Sure? Okay. Now, what am I really doing? So X is a random variable which has a standard deviation sigma. If I subtract a constant number from all the values of X, the standard deviation will not change. So the standard deviation of X minus mu will also be sigma. Right? Sure? Now we realize that if you multiply the standard each value of X by 10, the standard deviation get multiplied by 10. So if you multiply each value of X minus mu by 1 upon sigma, the standard deviation new variable will be the old standard deviation into 1 upon sigma, which will be what? 1. If X minus mu has the standard deviation sigma, if you multiply each value of X minus mu by 10, the standard deviation new variable will be 10 sigma. So if you multiply each value of X minus mu not by 10 but by 1 upon sigma, then the resultant standard deviation will be 1 upon sigma into sigma, which is 1. So any standardized distribution will have mean 0 and standard deviation 1. And if it is normal, then it will continue to be normally distributed. That is the standard normal distribution. Right? Sure? I will quickly show you that. Okay. So now, yes, we have got these two libraries. Yeah?
The
Okay.
screen is not visible.
Yeah, I'll just making it visible. Now it's visible? Yeah?
Yes, sir. Yes, sir.
Okay. Right. Now, let x be, so these are random numbers from the normal distribution. Right? Suppose I got so many random numbers. Say 1,000,000 random numbers from the normal distribution, mean 2 and standard deviation 2. Right? Okay? Right? Okay. Now, what I'll do is, I will kind of
So can you repeat this one? Is 2 and 2? Or both?
yeah, so this is the, so basically x is really 1,000,000 random numbers from the normal distribution with mean equal to 2, standard deviation equal to 2. Okay? Right? Sure? Now, say y is equal to x minus 2, right? Because we know the mean of x is 2, and divide by 2, right? Sure? And let me kind of cut this here. I don't want this here. And say x1. Yeah? Right? Okay. Now, just run this. Okay? And just say round mean x, round to the second digit. Yeah? Right? Round mean x, round to the second digit. Give you the original mean of x, which you know is 2. Right? Sure? We know y is standardized. So if you now do this, y is 0. Right? Yeah? Sure? Everyone getting this? Okay. Standard deviation of x. Okay, please say round, because you know that rounding off is important to the second digit, because computer 2, right? Standard deviation of y 1. Yeah? Right? राऊंड केलंस 2 डिजिट हां पण ते म्हणजे 1.99 काय तुझं कसे नाही हे केलंस ऑब्झर्वेशन्स किती घेतलेस 10 लाख चेक परत एकदा कर
So for y it is the mean is 0 and the standard deviation is 1.
Yeah, because we have standardized the data now, no? You understood why? Because y is now a standardized variable. Yeah? So if you now do this, P ggplot, right, x1 AES x is equal to x plus geom understroke density, right, fill is equal to blue, alpha is equal to 0.4 plus geom understroke density x1 AES x equal to y, fill is equal to pink, alpha is equal to 0.4. Bye.
There's a comma.
One comma before fill
Where?
What's the geom density?
in first line. 6, line number 6.
Fill charge.
Fill charge. हाँ right. परत नाही. Mapping geom density mapping will be created by AES.
Sir, there is a bracket after x, extra bracket after x.
Where? So here,
Before J, yeah.
no, that has to be there, no, because I'm telling you what is the AES, right? Yeah, sorry.
Can you go back to the code?
Yeah. So if you look at this now, this is the original distribution and this is a standardized one, right? Now, so the pink one is a standard normal, right? Now, even if you change the parameters here, the x distribution will change. But the standardized y distribution will remain unchanged.
So whatever change now, like which parameters?
No, so even if you change the parameters of x, the mean and the standard deviation, the y distribution will remain the same as long as you change them here also. Right? So if I make this say 2 and 4, right? So as long as I change this to 4, if I run this, see the original distribution will become much more flatter, but the standard normals remain the same. Right? The magician's cap has remained where it is. Like this. Right? Okay? Sure? So if this point, the point that I'm trying to make is that if you change the mean and the standard deviation, the blue distribution will change. But the pink distribution will stay where it is. So the cutoffs on the x-axis will also remain the same. If you want to cut off on the x-axis, points which contain 95% distribution, those points will still remain the same because the pink distribution is not shifting at all. Right? That is what
Why is it not changing the pink distribution? Like
because the pink distribution will always have the mean 0 and standard deviation 1, no?
Okay,
That is why, right? The pink distribution doesn't shift at all. So that's why when you standardize the distribution, the effect of the scale goes away. Right? Sure? Okay, now if you take this y distribution, we want to find the value such that 5% of the values are less than that value, which is called the quantile. Right? So if you say Q1 is quantile y, such that 0.05% of the values are less than 1. Right? And if you say Q1, what do you get? Minus 1.64. If I round it off, I will actually get minus 1.65, right? So if I just round it off to second digits, to 2 digits, right? Yeah? And if I say what is Q1, minus 1.65. So minus 1.65 is the value such that 5% of the values of the standardized distribution are less than that value. Right? So if I say quantile y 0.05, it tells me the value on the y-axis, on the x-axis, such that 5% of the values are less than that. Yeah? Quantile. If I want to find Q2, right? If I want to find Q2, round quantile y 0.95, right? So that 95% values are less than that, or 5% of the values are more than that, right? You will get, so if you get Q1, if you get Q2, right? Right? Yeah? Roughly minus 1.65 it should be, because it's a simulation. So, right? But minus 1.65 plus 1.65 is the, right? So if you actually draw this, so if you actually want to show this geometrically, graphically, yeah? Okay, so now I want to draw a vertical line in Google, right, on a ggplot. So let me find out how I do this. Go to Google, right, drawing a vertical line in ggplot2, right? What's the command? Geom understroke v line, right? Geom understroke v line, right? Okay, where do you want to give it? X-intercept. Right? So let me just copy this from here. And here I want this to be Q1, right? Let me make this size really small. Yeah, if I run this, okay, so size aesthetic is not there. So let's remove this size thing. Okay, we don't want that. It's called line width or something like that. Yeah? So you see the area in the middle of the two lines is 90% of the distribution. Area to the left of this line is 5%. Area to the right of this line is 5%. And if you change the original data, as you are standardizing it, these lines and this picture will remain unchanged. Right?
Can you repeat this once more?
Yeah, so basically the area to the left of this dashed line, first dashed line, is 5% in the pink curve, and area to the right of the second dashed line in the pink distribution is again 5%, right? And 90% of the area lies of the pink distribution lies between these two lines. Yeah? Right? Now do it.
I'm not getting this Q1 and Q2, like, I mean, I am trying to compare it, but I'm not getting this.
So Q1 is the 5% quantile, right? What's a 5% quantile? A number such that 5% of the values are less than that number. Yeah? So Q1 is equal to quantile, right? Y 0.05, and I want to round this off. I don't want it to be 2. Round this off to 2. You understood what's a 5% quantile, Pallavi? Value such that 5% of the values are less than that value.
Yes.
Right, so if your students have given an exam and 30% of students have scored less than 70, then 70 is the 30% quantile. Yeah?
So I'm not getting this, I'm not getting the result actually, when I compile this Q1 and Q2.
So did you add this? So Q1 and Q2, did you add these commands? Is everybody getting this now? Tell me, draw the lines for such that for the 95%, so basically draw the lines for 2.5% and 97.5% quantiles. Draw this graph for, tell me what are the 2.5% and 97.5% quantiles. So if Q1 is a 2.5% quantile and Q2 is 97.5% quantile, right? Tell me what those numbers are and show them pictorially. Q1 is 2.5% quantile, right? And Q2 is 97.5% quantile. So I want to draw two lines such that 95% distribution is between those two lines. 2.5% is less than the line on the left hand side. 2.5% is more than the line to the right hand side.
So I'm not getting this, I'm talking about the numbers.
Huh.
When I compare Q1 and Q2, when I run these blocks, I'm not getting how many observations in a line below 5%. That I'm not getting that output.
But you're getting the meaning, right? Are you getting the value for Q1 and Q2?
Yes.
So what are the values you're getting?
So I'm not, that values I'm not getting, but I'm getting the graph. I'm getting the graph, but once I compile this, I'm not getting this.
Show me, can you share your screen? Okay, so I'm not stop sharing. Pallavi will share. So you're getting those lines, no, Pallavi? Yeah, now run them. So just type Q1 and Q2 below. Just go to in the console, not there. Console is what is below, no? That blue thing which is coming, where the results are showing. It's saying console below, Pallavi, there. Below, in the window below. Not there. Come down, you see the window below? Hello, Yeah, here. Just type at the bottom Q1 and Q2. Just type Q1, not there. Yeah, there. Yeah, there. That's the console. Q1, just enter, -1. Q2. Q2, because Pallavi, you're doing 0.05, then the other will have to 0.95, right? Because 5% on this side, 95% on this side. So 0.95, yeah. Run that now. Q2. Yeah, type Q2 there. Not there, in the console. That is the editor. That, Q2. +1. Got this? Yeah? Thank you. Okay, so let's play around with this before we really start talking about tests of hypothesis now, right? Because the important idea is going to be then. If you remember, I told you in the last class that if you have a population that is normally distributed and the variance is sigma square, if you take a sample of size n, then the sample size is x bar. The sample mean has the same mean as the population mean, and the variance of the sample mean is the population variance divided by n. So if you have a normally distributed population and from which you have taken a sample of size n, then the sample mean x bar will also be normally distributed with mean mu and variance sigma square upon n. So, if you take x bar minus mu and divide by sigma divided by square root of n, the standard deviation, you will get a standard normal, which will lie between -1.96 plus 1.96. This can be used to take hypothesis tests about an unknown mean. So if you have a sample mean, you have to take a test about the population mean. Then you assume that this could have been the population mean. Then do x bar minus that mean. You have to know sigma square, population variance. So do square root of sigma by root n. And if that number lies less than -1.96 plus 1.96, reject the null hypothesis. Otherwise fail to reject the null hypothesis. That's the beginning of the Z test, right? But that we'll do in the next class, right? As long as I want you to be able to kind of do it for one, do the quantiles, draw those lines for 2.5%, 97.5%, 0.5% and 0.5%, so 99% of the distribution, right? Previously, if you remember, I don't know how many of you are old enough for those times, when we studied statistics, we had to get those textbooks with all these values written behind. Z table and all that. But now these guys are there, no? Any values you can find, critical values on this. So you don't need those tables anymore. Right? Okay, so those tables have thankfully become redundant, and because those tables were only done for 5%, 10%, we could only take hypothesis tests at 5% or 10%. Now here we can do at any point, right? Ultimately, whether you make a type 1 error, type 2 error, the risks have to be borne by the client. So what is the level of significance the client has to choose? This is tolerable type 1 error, not what statisticians like to calculate, right? So that is something that we can now do here. Sure? Any questions for the day? No? Is the idea of x bar clear? So I'll just take you through the thinking, right? Okay? I'll just take you through the thinking, right? So that very simple Z test, one of that we'll do, and then we can kind of strengthen it in the next class because still about 13 minutes to go. Right, so now I'm going to go back to my code. Right, okay. So now I'm going to get rid of all this. Okay, suppose I have some data. Right? Is some sample from a population. Okay, so this could be the sample of foot sizes. I am interested in finding out what is the average foot size of a male adult in Pune. Right? For some reason I am interested in finding the average foot size. You know, these are shoe numbers, for example. I want to find out what is the foot size of an average male in Pune. Yeah? Sure? Okay. Right. So, I collect a sample of whatever size. Okay? And suppose I know, what do I know? The population variance is 3. Right? Okay? My null hypothesis is size yeah? Sure? Right? Okay? Now, if my null hypothesis is true, I also know yeah? Sure? Right? So what do I know? What do I know? Sample mean x bar must be normally distributed yeah? Sure? Therefore, variance upon, of course, n, right? Sample means normally distributed with mean mu and variance sigma square upon n. And what is n in this case? 5, 6, 7, 8, 9, 10, 11, 12. Right? 12 in this case. Yeah? Therefore, x bar minus 5, which is my hypothetical mean. Therefore, if the null hypothesis is true, yeah? Right? Sure? Okay? So then 95% of times the values must lie between minus 1.65 plus 1.65. So I create a Z, which is what? Mean of x, which is coming from here, minus 5, which is known to me, divided by square root of 3 upon 12, right? Sure? I do this. What is the value of z that I get? Minus 5.99, right? So I know if the standard normal, if the data is actually standard normal, the value should lie between minus 1.95 plus 1.95. The chance that if the data are standard normal, a value is as small as minus 5.99 is very, very small. Right? Definitely less than 5%. So I reject the null hypothesis that the population mean is 5. Because, sure? So what you really look at the construction here of this test. Right, what have I done? I have taken x bar, right? Sure? X bar. What is x bar? Evidence. What is 5? Hypothesis. What is x bar minus 5? The gap between the evidence and the hypothesis. Why do I divide by standard deviation? I want this gap to be independent of units. So what I'm doing is, basically if this gap is too large to be credible, then I reject the null hypothesis. So all hypothesis tests are like this. There will be evidence compared to the hypothesis divided by the standard deviation so that we take care of units. It doesn't depend upon units of measurement. It's like this, no? If somebody tells me that my friend Avnish sings very well, right? And I ask him to sing, right? And if he sings horribly, right, what he sings is impossible to reconcile with the hypothesis that he's singing, he's a good singer, then I say, nahi yaar, Avnish tero gaana nahi aata hai, right? But if Avnish is singing, but thoda sa usme aage piche hai, possible that Avnish is not feeling too well today, etc. Right? So what I'm listening is not a great song, but the gap is not so high. Then I might say, okay yaar Avnish, to ho sakta hai, tera gala kharab hai, kal wapas gaega to we might sing differently, right? Sure? Yeah?
Sir, I have a question here.
Yeah, Pallavi.
Okay, so this is the hypothesis, right? I mean, so like this 5 is coming, that is a hypothetical number, like there is a population value, right?
Yeah, which I don't know what the population value is. I'm making a hypothesis. Could it be 5?
Okay.
And then I'm
So
saying,
how do you, like,
yeah.
Okay, so are you able to like come to a conclusion here, like whether we are rejecting the null?
So basically, look at what follows. I now know that if this is true, I know that the population variance is 3. Some reason, Brahmadeva has told me, right? Okay, my null hypothesis that the average foot size is 5. That's something I have in my mind. Right? That's a hypothesis I have, right? Sure? Okay. Okay. Population foot size, so I know that population foot size is normally receives mean mu and variance sigma square, in this case 3. Right? That's the population. So what do I know? From what we discussed in the last class, if you take a sample of size n from a population, then the sample mean has the same mean as the population mean, but the variance of the sample mean is the population variance divided by the sample size.
Yeah.
Right? So it means that the sample mean minus the population mean, right? Okay, so the sample mean x bar must be normally distributed with unknown mean mu, which is my hypothesis now, and variance 3 upon n, where n is the sample size and 3 is the population variance. Right? Which then means that, and we learned that if you have a normally distributed random variable, you subtract from it its mean and divide by the standard deviation, the resultant is a standard normal.
Yes.
So I take the sample mean, divide it from the hypothetical population mean, divide by the standard deviation, which is the variance of the original population, 3 upon 12, right? So this is the square root of 3 upon 12. 3 upon 12 was the variance of the sample mean of population size n, right?
Yes.
So this now must be a standard deviation normal. It will be a standard normal when this idea is correct. Because this is the only part which has come from outside.
Yes.
This has come from the data, this already I know.
Yes.
So the validity of the fact that this is standard normal depends upon the validity of by putting 5 here.
Okay.
Right? And 5 is my hypothesis. So what I'm really doing, x bar is my evidence, right? I went to all these people and looked at their foot sizes, and their foot sizes, the average foot size which I got from the data seems to be quite far off from 5. But I kind of divided by the standard deviation so that the units, whether I measure it in European foot sizes or UK foot sizes, right, or our Kolhapur foot sizes, right, it doesn't matter. right? Whatever the units of measurement are, right? So x bar minus 5. So if this is too small or too large, right? It says, okay, if this hypothesis is true, then there is only a 5% chance that these values will lay outside the minus 1.65 plus 1.65 interval. Yeah?
Yes.
Okay. Now what I find is this value is very small.
Yes.
So the chance of this value being generated, if my null hypothesis is true, is really small, definitely less than 5%. Right?
Yes.
So I say, okay, it doesn't seem likely that the average foot size of people in Pune is 5. Right?
Yes.
But if you change it to some other number, test the null hypothesis, the average foot size of people in Pune is 4. Tell me what you get.
It is minus 3.99.
Okay, so you still reject the null hypothesis, right?
Yeah.
Okay. Now if you want to test the average foot size of people in Pune is 3.
Okay. If it is 3. It is coming close to like minus 2.
Yeah. Because tell me what is x bar? Tell me what is the value of x bar now? If you just take x bar, what is that value? The mean of the sample, what is the value?
Mean of this sample.
At least mean of the sample 3.5 point कहते थे सर 5.4 is the sample mean, right? Is the sample mean 5.4? Sure? Right? Is the sample mean 5.4? Okay, right. $5.4, right? So if my actually observed foot size is 5.4 and if I am looking at 3, right, then the gap seems to be too large, no? Right? In fact, even for 5 the gap is too large because the variance is, pretty large, 3, right? Actually small in this case. If you reduce the variance, see what you get. Okay, so keep the foot size 5, keep the null hypothesis 5, right? And increase the variance of the population to 10. So, okay, I'm going back to the same exercise, right? Suppose I do the following now. Okay, my null hypothesis is, so I increase the population variance to say 10, right? My null hypothesis is that the mean of the is 5, but I've changed the population and I could reject it, right? I reject it in this case. Now suppose my population variance is 10. My Z value is 0.45.
Yes.
So I can't reject the null hypothesis now. Right? The same null hypothesis I could reject when the population variance was small. I cannot reject the null hypothesis, the population variance is large. What does that mean? It means that if there is not too much variation in the population, then a given x bar minus mu, even a small gap, right? My sample mean was 5.4, I was testing null hypothesis is 5. Even the small gap 5.4, the 0.4 was sufficient to say that the null hypothesis is not true because the data were not varying so much. But if the evidence is varying a lot, then the same gap might not be good evidence to say that actually the foot size is not 5. Because there are people with varying lots of foot sizes in the population. Whereas everybody in the population is the same kind of a thing, then small difference is also significant, right? If the population variance is large, you might fail to reject a null hypothesis. Second thing, important determinant is n. Larger the n, smaller will this denominator be. So bigger will z be. So you're more likely to reject a null hypothesis if you have large sample size. So it says if you have more information, you have more evidence to reject a null hypothesis. If you have low information, you cannot reject a null hypothesis. So you might be rejecting a null hypothesis not because it is true. You might fail to reject a null hypothesis simply because you don't have enough evidence. Right? That's why the sample size is important. If you are doing tests of hypothesis, you have to have sufficient evidence to say that the null hypothesis is not true. Right? If you go to a court of law, the null hypothesis that the person is innocent. And you really have to have a lot of evidence to say that this person is guilty. The more the evidence you have, the more strongly can you say that this person is guilty. Right? For a statistician, evidence is number of data points and number of independent data points. Right? All tests of hypothesis are exactly like this. The basic structure of a test of hypothesis: evidence, gap between the evidence and the null hypothesis, adjusted for the standard deviation. More the population variance, lower is the chance you will reject a null hypothesis. That is, greater is the probability you will create a type 2 error. Larger the sample size, lower is the probability of type 2 error. Tests which have a lower probability of type 2 error are said to be more powerful tests. So if you have more sample sizes, you will be able to reject a null hypothesis. There is a smaller chance of making a type 2 error. Right? So we'll stop at this point, folks, and do this a little bit more carefully in the next class. Next class we are going to learn Z, T, F chi-square tests. Right? And for that, Savita, I might require some derivations. So agar wo hoga na, or if there is a PDF of my textbook, nothing like that. आहे उदय मला म्हणजे I can just show you the formula. Then I don't, बोलली ना माझं पुस्तक नाही तर एकदम सोपे सोपे फॉर्म्युले आहेत त्याच्यामध्ये म्हणून बघ जमलं तर नाही तर अदरवाईज विल हॅव टू टाईप देम आउट बिकॉज देअर द डेरिवेशन्स आर रिअली वन स्टेप kind of thing. That book was written for people who have no background in econometrics, who get scared of numbers. For them, kind of a, but that's a very old textbook, 15 years now. It's, I think, quite out of print now. Okay, so thank you, folks. Thank you, everybody. Any questions, Pallavi? Any questions?
No questions. So we'll be repeating, this.
Yeah. 100% needs to be repeated, right? Sure. Thank you.